Welcome to the 6th video of this semester. Today we're going to be talking more about the LM function. We'll be doing some null models and one parameter intercept only models. So if you haven't installed the LM support library, you should go ahead and install it. It has a lot of great functions for linear modeling that we'll be using as we go further along through the semester. I have a note here about the intercept is the mean of the outcome when all the parameters equal 0. This is here mostly as a reminder to mention it to you all. But this idea here is going to be just relentlessly hammered into you. One of the great things about this linear modeling approach that we're doing is that sure, it's taken us this many weeks into the semester to start getting into the first and most basic models, but having a real firm grounding in understanding basic linear models makes it really easy to expand the general linear model, which is really flexible. So it's one of the really nice things. And so as we go on, we're always going to be interpreting things the same way because we're always using the same approach. And ultimately, all it comes down to is you just have to remember that the intercept is the mean of the outcome when all of the parameters in the model are 0, regardless of how many parameters you have. Just set them all to 0 and calculate the mean of your outcome, and that is your intercept. So that'll make more sense as we get into models with more parameters in it, but I'm going to go ahead and start hammering that in now, and you'll hear that a lot. So we're going to load the tidyverse and LM support libraries, and then as a reminder, this option scipin equals 10 is simply changing it to where I don't get scientific notation. And so we're going to read in the same bias data set that we did last week, and then as we always do whenever we read in data, you should always explore the data, take a look. Even if it's a file that you think you recognize, go ahead and take a look, because you may discover that in this one we're doing it's the IAT data set, but it actually has additional variables that weren't in it when we used it before. So maybe the data isn't what you think it is. It's just a good habit to always take a glimpse at your data, look at your descriptives, structure, the number of variables, number of observations, all that stuff. Make sure that it's what you're expecting. In this case, it is the same data that we used last week. So it's this IAT scores with that implicit attitudes, and we want to see if there's a change from people's baseline IAT scores to their week 8 base score. So we'll have to create that IAT change variable again. And then if we look at our descriptives, we still see that there's still only the one condition. We've got these 4 concern scores that we haven't talked about, between 1 and 10, and our 3 baseline, our 3 IAT scores, baseline, week 4, and week 8 IATs. So we'll go ahead and create that IAT change variable, which is just the week 8 IAT score minus each baseline IAT score. So we use mutate to create that function and store that back over our data. And so now when we look in our bias data, we can see that we do have that IAT change variable in there. So first we're going to do this all by hand like we did last week, but since this is just a reminder of what we did last week, we're going to do it all in one fell swoop here. And so we're going to create some new variables, predict.mean, which is we just set as the mean of the IAT change variable that we created. Error mean is going to be that IAT change variable that we created minus the predict mean variable that we created here. Square error mean is going to take that error mean variable that we just created and square it. And then we're going to do predict 0 and just set the value to 0. Same thing, error change is the IAT change variable that we created minus that 0 that we created here, and then squaring that to get square error 0. So Now when we look in our data set, we take a glimpse, we can see that we've created that IAT change variable, and then here is where we predict this mean value for each participant. Here on predict 0, we just predict 0 for each one. Then we find the difference between that prediction and the actual value and get error mean. Or here we find the difference between the actual value and this prediction of 0, and then just square those accordingly. So we're all tracking on what all those variables are. So then to manually calculate our f-test, what we have to do is, again, we use in-row to pull the number of observations we have. So now we have an object in our environment, you can see down here, that is called n, and it says 78L. As a reminder, that L is how R indicates that this is the integer 78. And so then here, all we do is we take that, we take our bias data frame, and we're just going to select the square error mean column, and then pipe that into the sum function. And then here do the same thing but the square error 0 function, and we're going to save that as SSE mean and SSE 0. And so we now have those two values down in our environment as well, where SSE mean right here 7.08 and SSE 0 is 11.63. So then to actually do the f-test, here's the formula again, and the way that I set up this formula is that .c means compact and .a means augmented. So this is the SSE compact minus SSE augmented over the number of parameters in the augmented model minus the number of parameters in the compact model, and then all of that is over the sum squared errors for the augmented model over n minus the number of parameters in the augmented model. As a reminder, this n here is 78. We already pulled that in. And then this portion here together is the DF numerator, and this portion here, n minus the number of parameters in the augmented model, is our degrees of freedom for our denominator. So that's where here it's finding out how many more parameters are in the augmented model than the compact model, and the denominator is how many more parameters could we have theoretically included. And so now I've stored, if I run those two lines, I've now actually stored objects in the environment called DF numerator and denominator in SSE mean and SSE 0. So if I do SSE 0 minus SSE mean here, it will compute that for me. And then my DF denominator is 1, so this portion here will be that 4.545 if I didn't highlight too many parentheses. And then down here we have our SSE mean and our DF denominator. And so when we run that entire line, it will compute it all together and give us our f-stat of 49.365. 366 if you want to round. So now that we have our f statistic, we can put that in this PF function along with our DF numerator denominator, and we'll tell it lower tail equals false to tell it we want to do a one-tailed test here, and we get our p-value that is less than 0.001. And if you put all this together, you would report f1, 77, so your degrees of freedom there, numerator denominator, equals 49.37. P is less than 0.001, and that's just how you would report this f-test. So now to see how we would do that as using linear model, and again, like some of this is just a reminder, is that we in the LM function, it is the outcome, then the tilde, meaning regressed on or predicted by, and then here we put in the digit 1, and so that digit 1 tells R, it reads that as the intercept. So IAT change regressed on the intercept, and data equals bias. So just for this week, I'm going to avoid piping into LM just to make sure things are clear for everybody, although there is good reason to make sure that you understand how to pipe things directly into the LM function. So now we have this model that we are fitting as an object that I'm naming mod.mean. Keep in mind you can name these whatever you want. You don't have to follow my exact naming conventions, and if you change the name of this object, that just means that you have to change the name anywhere else that it appears in the script. I just want to make sure that nobody's getting confused as to how I name things and thinking that any one thing is set in stone. So we've now created this linear model object called mod.mean, and if you look over here you see a list of 11, and so if we look at the help file for LM and then click, I have this comment fitting linear models, because when you just do the question mark it'll have both of these pop up. We don't want this VGAM library, we want the fitting linear models, and this gives you a lot of information, but what I want to scroll down to just a brief look at is where it says value. And then down here it says that an object of class LM is a list containing at least the following components. And so it has these different things in here. For instance, the coefficients, a named vector of coefficients, the residuals, fitted values, etc. And so you can call, like, these are all part of this mod mean LM object that we created. And so you can call those with a $sign just like you would calling a column out of a data frame. So if we do mod.mean $sign residuals, it will output the residuals for each observation, or the fitted values is another term for the predicted values. So if we run mod.mean $sign fitted values, it's going to give us the prediction for each observation. And so notice how these line up with our manual calculations. So I'm creating a tibble that manual.predicted and manual.resid are just the predict.mean and error.mean variables that we created by hand earlier. And then lm.predicted and lm.resid are just calling from the actual LM model object that we created right here. So calling this object the fitted values and the residuals, and when we run that we can see that this gives us the exact same values. So all that LM command here does is use the intercept to predict, so it has that same predicted value for each one, which then gives us the same residuals for each one, etc. You can call the coefficients of the model using the coef function, COEF, and so we can see that our intercept is negative 0.2413 ... And as we've discussed, the intercept of an intercept-only model is the mean of the outcome variable, and so that's why you'll sometimes hear this called a mean-only model, or an intercept-only model. But so if we check there, we can see that if we just look at the mean of IAT change, that we get that same value as that intercept. To manually create a null model, a model with no parameters in it, you have to explicitly tell R to leave that one parameter off, and you can do that by either including the term 0, which means no parameters, or by negating the 1 by adding the minus sign in front of the 1, so telling R not the intercept. Because remember that the 1 means the intercept. When you're in LM, don't think of 1 as the number 1. Think of it when you see 1, think intercept. So this means IAT change regressed on not the intercept, which means nothing, that there are no parameters in this model. Although this would be, if you ran it instead as IAT change tilde 0, that would be functionally the exact same as regressed on this -1, not an intercept. So now if we look at the coef function, look at how many coefficients we have in this model, you can see we have 0 coefficients in this model because we have 0 parameters. So now when we look back at our model summaries, we can see here that it gives us some information about our residuals, the min, the first and third quartiles, median, and max. It gives us our parameter estimate for our intercept, which again you can see that is the coefficient for the estimate is the coefficient. So that again is our mean. It also gives us a standard error, a t value, which again is if you square it is your f, and it gives us a p-value. But notice in this residuals output here, where it gives you that information, if you wanted that information, you could get it yourself. Because here, this error mean, recall, is what we computed up here. We created error mean. And if we take that error mean variable, and we find the min, use this quantile function and tell it probs equals 0.25. That's telling it the first quartile. The median, then Q3 is the third quantile, and then max. And so if we run this function, we get the same output as the residuals here in our summary. So we can see that we get negative 1.10 and negative 0.335, and then our median. So all of this lines up. So again, when we look in our summary and we see this information, I'm just trying to connect dots here to show you where those numbers are coming from so that you understand your output here. So then when going back to our summary, again, notice that the coefficient for the estimate of the intercept is the mean of the outcome. It is that bias change. If we take the square root of our f-stat that we computed earlier, then that will give us our t, or at least the absolute value of our t. Said another way, if you square this t, then you don't have to worry about the absolute value, because negative 7 times negative 7 is going to give you positive 49 for that f-stat. Our p-value here that we computed earlier is the same that our summary gives us, and then also our degrees of freedom denominator is the same that our summary gives us. But what about the null model, though? So if we look at our null model, it tells us no coefficients, because again, there are no parameters in this model to estimate. It is a null model. But then when we look at our residuals based on the error 0 variable that we created instead of the error mean variable that we created, we can see that's where it's still getting these things from. So from that, you can tell that the LM function, when we put in that -1, not the intercept, or the 0, all it does is it includes 0 as the prediction and then computes the residuals accordingly. So here's where we manually made every row 0 and then said, all right, now find the difference between that 0 and the actual value, and then LM did the exact same thing. Few last things here. So instead of base R's summary function that we've been using like this, and I'm actually going to run that based on the mean model. So instead of that, there's a function in the LM support library that's called model summary. That's with a capital S on summary, and it has a few nice features that should have an S. Specifically, the ability to report F instead of T. It reports your sum of squared errors, and it reports your R squared, which I don't know how much you know about yet, at least not while I'm recording this video. but it's a measure of effect size, and one that's often used. But anyway, so if we run just model summary with the same model as our regular summary, we can see that we largely, at least as far as our coefficients and stuff, it will be the exact same. The biggest difference is that model summary does not include this residuals descriptive information, and then, like I said, this does include our sum of squared errors instead of the residual standard error. And it also will report r squared with it. But then notice that t is also, like I said, it's you can have model summary report it directly as an f instead of as a t. So if you include this argument t equals false, then instead of reporting that t, you can see that model summary will then report that as an f instead. And now when we look at our fstat and our sum of squared errors for the mean, we can see that now we don't have to do any math to convert to make sure that our numbers are lining up and say, oh, well, is negative 7.026 squared equal to the fstat that we manually calculated? We can just look and say, yep, this is this fstat that we manually calculated. And then again here it tells us the sum of squared errors lines up with what we manually calculated. As far as the model 0, the null model, again, there are no coefficients in this model, but I just wanted to point out that it did say that our sum of squared errors is 11.6, and when we look at our manually computed ones, that is what we find the sum of squared errors to be. I personally prefer the model summary function to the base R summary function, so that's what you're going to see me using from here on out now that it's been introduced to you. But if using base R summary is more of your flavor, then more power to you, and have a great time using that function. So the last thing that we're going to talk about here is comparing models, and so we'll look at two functions, ANOVA and something called model compare. So when we look at the ANOVA function, and this is the ANOVA that surely you have all heard of before, just that analysis of variance. But whenever you have, whenever you're doing the ANOVA, if you give it a single argument, it will produce a table. It does an analysis of variance that tests whether the model terms are significant. But as Bill alluded to in class on Monday, it tests whether whatever you put in it, it tests that against an intercept-only model. And that's important, and we'll talk more about it here in just a second. But if you put in 2 or more objects, then ANOVA will test the models against each other in sequential order. So if we just put this our null model mod.0 into the ANOVA, it'll give us our sum of squared errors and our mean square, but it doesn't give us an f-test here. Same thing for the intercept only model, but that's because these models, again, this ANOVA function, it tests the models against a null model, or excuse me, against an intercept only model, and since this is the intercept only model or is less than an intercept only model, that test can't be computed. So later, once we have additional parameters and we have more parameters than the intercept only, this will change a little bit, and even just putting that one model object inside ANOVA will report some sort of f-test, but for now it won't. But when we put in 2 models, so if we add in the ANOVA function our null model, comma, the intercept only model, or also our compact model versus our augmented model, now it compares those 2 models against each other, and this should look a lot like, or this should feel familiar and look a lot like the ANOVA tables that I'm sure you ran up against as an undergrad, just when you're talking about that basic ANOVA F table. And so what this is doing is it's testing Alright, so if we take this first model here, which model 1 is that intercept, or is the null model, that there is no intercept, and if we look at what its degrees of freedom and what the error is of that model, then once we look at this second model, which in this case is the intercept only model, what's the error, what's the degrees of freedom, and did we get a significant reduction in error that is worth the additional parameter or parameters that we put in? And in this case, yes, it is, because it's a significant drop, which it's completely uninteresting, and a no intercept model doesn't really make a lot of sense, as Bill talked about. I can't spell, and the only time I've ever even heard of anybody discussing intercept models that leave off intercepts is dealing with like mixed effects models and other more advanced techniques that you'll talk about in later courses, but it won't be in this course at all. But going back to the model summary, I want to run that again so that we have it fresh. And then I want to talk about this model compare function, which does direct model comparisons. All you do is you enter in your compact model followed by your augmented model, and it will calculate that f-test for you and do that model comparison. Plus, it reports the sum of squared errors for your compact and augmented models, what your delta r squared or your change in r squared is. In this case, it's such a small number that it just rounds to 0, but that's not usually the case. And this one will also report partial eta squared, which is that PRE variable that your book authors love so much. But so just in conclusion, like this gives you all the information from your summary, except for it doesn't give you the actual coefficient estimate. And so if you're not interested in estimating those coefficients, and if you don't need that information and all you're doing is testing for, is there a significant difference, or a significant reduction of error based on X, and if all you're looking for is the f-test on that, but you don't care what the actual values are, then you can skip the summary and just look at your actual model comparisons. Oftentimes, at least in my research, like I am interested, at least to some degree, in like what those actual estimates are, and so like I do need to look at this. But this model comparison, a nice thing about it is that it allows you to test nested models, where you can just change in what models are in there, and your compact model will have all of your augmented model will have all of your variables of interest, and then with your compact model, you're taking off one specific focal parameter. So if I'm including 4 different parameters, and let's say that color of the room is like my focal parameter, it's what I'm really interested in, then I simply test a model with all 4 of my parameters, including color of the room, and then my compact model will simply take off color of the room. And so when I compare a model with and without that one specific thing and see, is there a significant reduction of error, that's how you can know that, hey, this one particular parameter is significant and meaningful. And so that's where you get, like, in your, if this had 3 additional rows for the other 3 parameters, including 1 row for the color of the room, then color of the room would have significant stars next to it. That's where that's coming from. But all of this will continue to make more and more sense, because we're going to keep doing more and more of this same thing, and just kind of adding on pieces bit by bit by bit. But in short, that concludes this week's video. If you have any questions, just let me know.